What if I told you that right now, at this very moment, you're aging faster than astronauts orbiting above your head on the International Space Station? What if I told you that there exists a way, a real scientifically proven method to stay young while your twin brother grows old and grey? What if I told you that speed, the simple act of moving fast, could become your personal fountain of youth? This is not science fiction. This is not fantasy. This is not a dream someone had after watching too many space movies. This is real. This is proven. This is one of the most mind-bending truths about our universe that most people never learn about in school. Imagine this scenario with me. You're 25 years old, you step onto a spacecraft, you wave goodbye to your friends, your family, everyone you've ever known. The engines ignite with tremendous power. You accelerate away from Earth, faster and faster, until you are traveling at nearly the speed of a light itself. You spend what feels like 5 years on this incredible journey through the cosmos. 5 years of your life, 5 birthdays, 5 years of memories, and then you return home. You step off your spacecraft, now 30 years old, ready to reunite with everyone you left behind. But something is wrong. Something is very, very wrong. The faces looking back at you are not the faces you remember. Your childhood friends are now 50 years old. Your younger siblings have grey hair. Your parents are gone. The world has moved on by decades while you experienced only 5 years. How is this possible? How can time itself play such a cruel and beautiful trick? Before you dismiss this as impossible, before you shake your head and say this sounds like something from a movie, let me share some facts with you. Real facts. Verified facts. Facts that will make you question everything you thought you knew about time itself. Fact number 1. The global positioning system in your phone, the GPS that tells you where the nearest coffee shop is, has to account for time dilation effects. If the engineers did not program corrections for this phenomenon, your GPS location would be wrong by kilometers every single day. Not meters, kilometers. The GPS satellites are experiencing time differently than you are right now, and this is not a glitch. This is physics. Fact number 2. The Parker Solar Probe, the fastest human-made object ever created, traveling at speeds that would take your breath away, experiences measurable time dilation. We can detect it. We can measure it. It is real. Fact number 3. A Russian cosmonaut named Sergei Krikalev has spent so much cumulative time in orbit, traveling at tremendous speeds around our planet, that he is now 0.02 seconds younger than he should be. He has literally traveled into the future by a tiny amount. His atoms, his cells, his entire being experienced less time than everyone on Earth below him. Fact number 4. If you could build a spacecraft capable of traveling at 99.9% the speed of light, and you traveled in that spacecraft for just 1 year by your own clock, 22 years would pass on Earth. 22 years. Your 1 year equals everyone else's 22 years. Fact number 5. Right now, particles called muons are raining down on Earth from space. These particles have such short lifespans that they should decay and disappear long before reaching the ground. They should never make it to our detectors, but they do. They arrive at our instruments despite the impossibility of their journey. Why? Because they are traveling so fast that time slows down for them. They experience less time during their journey, allowing them to survive long enough to reach us. This is happening right now, all around you, all the time. If you are still watching, if your curiosity has been sparked, if you feel that itch in your brain that comes when you encounter something truly profound, then you are in the right place. Because today we're going to take a journey together. A journey through the deepest mysteries of space and time. We're going to understand not just what time dilation is, but why it happens. We're going to do actual calculations together, real math that reveals the secrets of the universe. We're going to explore paradoxes that confuse the greatest minds in physics for decades. We're going to see how this affects real space missions and what it means for the future of humanity among the stars. And finally, we're going to answer the question that might be burning in your mind right now. Could you actually use this to live longer? Could you cheat death itself by moving fast enough? I want you to do something for me right now. In the comments below, I want you to guess. How fast do you think you would need to travel to age at half the rate of someone standing still on Earth? Take a guess, write it down, we will reveal the answer together, and I promise you it will surprise you. If this kind of cosmic mystery excites you, if you want to understand the deeper secrets of time itself, hit that like button. It tells me that you want more content like this, that you want to explore the universe together. and subscribe to this channel because we are about to break your understanding of reality in the most beautiful way possible. Now, before we can understand why moving fast affects time, we need to step back and ask a more fundamental question. What is time? What is this thing we measure with clocks and calendars? What is this invisible river that seems to carry us from birth to death, from past to future? For most of human history, the answer seemed obvious. Time was constant. Time was absolute. Time flowed at the same rate for everyone, everywhere, always. A second in Paris was the same as a second in Tokyo. A second on a mountaintop was the same as a second at the bottom of the ocean. A second for you was the same as a second for me. This idea was so intuitive, so natural, that it did not even seem like an assumption. It seemed like simple truth. Sir Isaac Newton, one of the greatest scientists who ever lived, built his entire system of physics on this foundation. He called it absolute time. In Newton's universe, there was a cosmic clock somewhere, ticking away uniformly, marking the same moments for everything and everyone in existence. Space was also absolute. A ruler in London measured the same distances as a ruler in Beijing. The universe was like a giant stage, fixed and unchanging, upon which all the events of reality played out. This framework worked beautifully. It explained the motion of planets. It described how objects fall. It allowed us to predict eclipses and build bridges and understand the mechanics of everyday life. For over 200 years, Newtonian physics reigned supreme. It was not merely successful, it was triumphant. But there was a problem, a small crack in the foundation that would eventually shatter everything. In the late 1800s, scientists were obsessed with light. They knew that light behaved like a wave, similar to sound waves or water waves, and all known waves needed a medium to travel through. Sound waves travel through air. Water waves travel through water. So what did light waves travel through? Scientists proposed a substance called the luminiferous ether. This ether was supposed to permeate all of space. It was providing the medium through which light could propagate. It was invisible, weightless, and everywhere. It seemed like a reasonable hypothesis. But then came the experiments. Two American scientists, Albert Michelson and Edward Morley, designed an incredibly clever test in 1887. If the Earth was moving through the ether as it orbited the Sun, then light traveling in the direction of Earth's motion should appear to move at a different speed than light traveling perpendicular to that motion. It was like walking on a moving walkway at an airport. Your speed relative to the ground depends on whether you walk with the walkway, against it, or across it. Michelson and Morley built an instrument called an interferometer that was sensitive enough to detect these tiny differences in light speed. They ran their experiment. They waited for results. And what they found shocked the scientific world. There was no difference, none at all. No matter which direction they measured, no matter what time of year it was, no matter how Earth was oriented in its orbit, the speed of light was always exactly the same. This was impossible. It violated everything scientists thought they knew about how waves worked. It violated basic logic about relative motion. If you're driving a car at 50 kilometers per hour and you throw a ball forward at 10 kilometers per hour, the ball moves at 60 kilometers per hour relative to the ground. This is obvious. This is intuitive. This is what everyone expected to happen with light. But light did not cooperate. Light simply refused to follow the rules. A beam of light traveled at exactly the same speed whether you were moving toward it, away from it, or standing perfectly still. The experiment was repeated. The instruments were refined. The results remained the same. Something fundamental was wrong with the way scientists understood the universe. Enter a young man working at a patent office in Switzerland. His name was Albert Einstein, and in 1905 he would change everything. Einstein did something remarkable. Instead of trying to explain away the strange behavior of light, instead of searching for some hidden variable or experimental error, he accepted it. He took the constancy of light speed not as a problem to be solved, but as a fundamental truth about reality. He asked himself a simple but revolutionary question. What if the speed of a light really is the same for all observers? What would that mean for our understanding of space and time? The answer would demolish 200 years of physics and birth an entirely new conception of reality. Einstein proposed two simple statements, two postulates, that would become the foundation of his special theory of relativity. The first postulate states that the laws of physics are the same in all inertial reference frames. An inertial reference frame is simply a perspective from which you are not accelerating. If you're sitting in a train moving at constant speed, you are in an inertial reference frame. If you are floating in space far from any gravity, you are in an inertial reference frame. Einstein said that no matter which inertial reference frame you occupy, physics should work the same way. You cannot do any experiment to determine your absolute velocity through space, because there is no such thing. All uniform motion is relative. The second postulate is the bombshell. The speed of light in a vacuum is constant for all observers, regardless of their motion relative to the light source. This does not seem revolutionary at first glance, but follow its implications. If you are standing still and measure a beam of light, you get approximately 299,792,458 meters per second. If your friend is flying toward that same beam at half the speed of light and measures it, they also get exactly 299,792,458 meters per second. Not faster, not slower, exactly the same. Think about how bizarre this is. In everyday life, speeds add and subtract. If two cars are driving toward each other at 50 kilometers per hour, they approach each other at 100 kilometers per hour combined. But light does not work this way. Light always arrives at the same speed, no matter how fast you chase it or run from it. Einstein realized that for this to be true, something else had to give. If the speed of light is truly constant, then the only way to preserve this constancy is if space and time themselves are flexible, if time can stretch and compress, if length can contract and expand, if what seems solid and fixed is actually malleable and relative. This was the revolutionary insight. Light speed is constant. Everything else, including time itself, must adjust to make this true. When Einstein first published these ideas, many scientists rejected them. The concept seemed too strange, too counterintuitive, too radical. But as more physicists worked through the mathematics, as more predictions were tested and confirmed, it became undeniable. Einstein was right, Newton was wrong, at least about the nature of space and time. The universe was far stranger than anyone had imagined. Now, let us dive deeper into this strangeness. Let us understand exactly how moving fast affects the passage of time. I want to walk you through one of the most famous thought experiments in all of physics. It is called the light clock, and once you understand it, you will understand time dilation at its most fundamental level. Imagine you have a clock that works in a very simple way. It consists of two mirrors, one at the top and one at the bottom, separated by some distance. A pulse of light bounces between these two mirrors. Every time the light completes a round trip from bottom mirror to top mirror and back again, the clock ticks. This is a perfectly valid clock. It measures time just as well as any other clock. Now, imagine this light clock is sitting in a spaceship that is stationary relative to you. You watch the light pulse bounce straight up and down, tick, tick, tick. The path of the light is simple and direct. But now imagine that spaceship begins moving sideways at tremendous speed. What do you observe? From your perspective, standing still and watching the spaceship zoom past, the light pulse cannot simply bounce straight up and down anymore. Why? Because while the light is traveling from the bottom mirror to the top mirror, the entire clock has moved sideways. The light must travel diagonally to reach the top mirror, and while it returns from the top mirror to the bottom mirror, the clock has moved even further sideways. The light must travel diagonally again. The path of the light, as seen by you, is a zigzag pattern, and here is the crucial point. A zigzag path is longer than a straight up and down path. We know that light travels at a constant speed. It cannot speed up to cover the extra distance in the same amount of time. So what happens? The only possibility is that it takes longer. From your perspective, watching the moving spaceship, the light pulse takes more time to complete each round trip. The clock ticks slower. But here is where it gets truly mind-bending. From the perspective of someone inside the spaceship, someone moving along with the clock, the light pulse is still just bouncing straight up and down. For them, the clock ticks at its normal rate. Nothing seems strange or different. Both perspectives are correct. Both are equally valid. There is no absolute truth about how fast the clock is ticking. It depends entirely on who is asking the question. For the stationary observer, the moving clock runs slow. For the moving observer, their clock runs perfectly normally. This is time dilation in its purest form. It is not an illusion. It is not a trick. It is the actual behavior of time itself. When you move through space, time slows down for you relative to someone who is not moving. Let me give you the actual mathematics of this phenomenon. Under there is a formula that tells us exactly how much time slows down at any given speed. It involves something called the Lorentz Factor, named after the physicist Hendrik Lorentz, who discovered it independently before Einstein gave it deeper meaning. The Lorentz Factor is represented by the Greek letter gamma, and it equals 1 divided by the square root of 1 minus the quantity velocity, squared divided by the speed of light squared. Written mathematically, gamma equals 1 over the square root of 1 minus v squared over c squared. This formula is the key to understanding time dilation quantitatively. Let us see what this formula tells us at different speeds. If you're travelling at 10% of the speed of light, which is about 30 million meters per second or 67 million miles per hour, incredibly fast by human standards. The Lorentz factor is about 1.005. This means time for you is passing at about 99.5% the rate of someone stationary. A tiny difference, barely noticeable over a human lifetime, but now let's increase the speed. At 50% the speed of light, the Lorentz factor rises to about 1.15. Time for you is now passing at about 87% the normal rate. For every year you experience about 1 year and 2 months pass for someone standing still. The difference is becoming significant. At 90% the speed of light, we start seeing dramatic effects. The Lorentz factor is about 2.3. Time for you is passing at only about 44% the normal rate. For every year you experience, more than 2 years pass for stationary observers. You're aging at less than half the rate of everyone else. At 99% the speed of light, the Lorentz factor jumps to about 7.1. Time for you crawls at only about 14% the normal rate. For every year you experience, over 7 years pass for everyone else. 1 year of your life equals 7 years of theirs. At 99.9% the speed of light, the factor is about 22.4. Time for you is at about 4.5% the normal rate. Your single year equals over 22 years for stationary observers, and at 99.999% the speed of light, the factor reaches about 707. Your 1 year equals 707 years for everyone else. You could leave Earth for what feels like a weekend and return to find everyone you ever knew has been dead for centuries. Do you remember the question I asked you at the beginning? How fast would you need to travel to age at half the rate of someone standing still? Now you can calculate it yourself. Half rate means the Lorentz factor equals 2. Working backwards through the formula, this occurs at about 86.6% of the speed of light. That is approximately 259 million meters per second. At this speed, for every year you experience, 2 years pass for everyone else. Were you close in your guess? Let me know in the comments. Notice something crucial about this formula. As velocity approaches the speed of light, the Lorentz factor approaches infinity. This means time dilation becomes more and more extreme as you get faster and faster, but you can never actually reach the speed of light because the factor would become infinite. At light speed, time would stop entirely, and beyond the speed of light, you would get imaginary numbers, indicating that such speeds are physically impossible. The speed of light is not just a very fast speed, it is the fundamental speed limit of the universe, woven into the fabric of reality itself. Let me do some concrete calculations with you so this becomes real and tangible. Imagine a spacecraft capable of traveling at 80% the speed of light. At this speed, the Lorentz factor is about 1.67. Now imagine this spacecraft takes a journey that lasts 10 years according to the clocks on board. 10 years of ship time. How much time passes on Earth during this journey? We multiply the ship time by the Lorentz factor. 10 years times 1.67 equals about 16.7 years. So while the astronauts experience 10 years, celebrate 10 birthdays, age 10 years, the people back on Earth experience nearly 17 years. The astronauts return to find Earth has aged almost 7 years more than they have. Now let us push further. Imagine a spacecraft traveling at 99% the speed of light for just 1 year of ship time. The Lorentz factor at this speed is about 7.1. 1 year times 7.1 equals about 7.1 years on Earth. The astronauts experience 12 months while Earth experiences 85 months. And for the most extreme example, imagine traveling at 99.9999% the speed of light for 1 year. The Lorentz factor at this speed is over 7,000. 1 year of your time equals over 7,000 years on Earth. You could leave today, spend what feels like a single year exploring the galaxy, and return to Earth in the year 9000. Everyone you ever knew, every nation that exists today, every language currently spoken, all of it would be ancient history. You would step out of your spacecraft into a world utterly unrecognizable, carrying memories of a civilization that existed before the pyramids seem recent by comparison. I hope you can feel the weight of this realization. This is not speculation. This is not theory waiting to be proven. This is established physics, tested and confirmed countless times. Used in technology you rely on every single day. The universe genuinely works this way. Time genuinely flows at different rates depending on how fast you're moving. And this raises a profound question that we must address. Why? Why does the universe work this way? What is it about the fabric of reality that makes time flexible rather than fixed? This is where we need to go deeper, beyond just knowing the what, and into understanding the why. And the answer lies in one of Einstein's most beautiful insights, the concept that space and time are not separate things at all. You see, we naturally think of space as one thing and time as another. Space is where things exist. Time is when things happen. They seem fundamentally different. You can move freely through space in any direction, left, right, forward, backward, up, down. But you seem to move through time in only one direction, always forward, always at the same rate, helplessly carried from past to future. But Einstein showed us that this intuition is wrong. Space and time are woven together into a single entity called space-time. It is a 4-dimensional fabric, 3 dimensions of space and 1 dimension of time, all interconnected, all part of the same underlying reality. Here is the key insight that unlocks everything. Everything in the universe is always moving through space-time at the same speed. That speed is the speed of light. Always, without exception. You might object and say that you're sitting still right now, reading this, not moving at all. But you are moving. You are moving through time. Every second you travel 1 second further into the future. That motion through time, that is your movement through space-time, and that motion happens at the speed of light. Think of it this way. You have a cosmic speed budget. That budget is exactly the speed of light, and you can spend it however you like, but you cannot exceed it. If you are stationary in space, your entire budget goes toward moving through time. You move through time at the maximum possible rate. You age as fast as you possibly can. But what happens when you start moving through space? You must borrow some of that speed budget from your motion through time. Some of your cosmic velocity is now spent moving through space instead of through time. The faster you move through space, the more budget you borrow from time, and the more budget you borrow from time, the slower you move through time, the slower you age, the slower your clocks tick. This is why time dilation happens. When you travel at 90% the speed of light through space, you are spending 90% of your cosmic budget on spatial motion. Only a small fraction remains for temporal motion, so your clocks run slow, so you age slowly, so time dilates. And at the speed of light itself? If you could somehow travel at exactly the speed of light through space, you would spend 100% of your budget on spatial motion. There would be nothing left for temporal motion. Your clocks would stop entirely. You would not move through time at all. This is the condition of photons, particles of light. From a photon's perspective, if we can even use such a phrase, time does not exist. A photon emitted from a distant star traveling billions of years from our perspective experiences no time whatsoever. The moment of emission and the moment of absorption, separated by eons from our view, are the same instant from the photon's perspective. Birth and death, beginning and end, simultaneous. This cosmic speed budget analogy is not just a metaphor, it is mathematically precise. The Lorentz Factor we discussed earlier captures exactly this relationship. When you increase your speed through space, your rate of travel through time decreases in exactly the way the formula describes. The total magnitude of your velocity through space-time remains constant at the speed of light. This also explains why nothing with mass can reach the speed of light. As you accelerate, as you try to spend more and more of your budget on spatial motion, something else happens. Your mass effectively increases. The energy required to accelerate you further increases. As you approach the speed of light, your effective mass approaches infinity, and the energy required to push you any faster also approaches infinity. You would need infinite energy to reach light speed. This is impossible. The speed of light is not just fast, it is a fundamental barrier, an asymptote that massive objects can approach but never reach. Only massless particles like photons can travel at exactly the speed of light. They exist at that special point where all of their spacetime velocity is through space, none through time. They are, in a sense, frozen outside of time entirely. What would happen if something could exceed the speed of light? In our current understanding, this would break causality. Effects could precede causes. You could, in principle, send a message to your own past. Paradoxes would arise. The logical consistency of the universe would unravel. Most physicists believe that faster-than-light travel and communication are genuinely impossible. Not just technologically difficult, but fundamentally forbidden by the structure of reality. The speed of light is not just a speed limit like the one on a highway, which you can break if you are willing to risk a ticket. It is more like a mathematical truth, woven into the equations that describe existence itself. At this point, I want to pause and acknowledge something. If you have made it this far, if you're still engaged and thinking about these ideas, you're doing something remarkable. You're wrestling with concepts that confused and amazed the greatest physicists of the 20th century. Time dilation is not intuitive. For all it violates everything our everyday experience teaches us about the world. But the universe does not care about our intuitions. It operates according to its own rules, rules we discovered through careful observation and rigorous mathematics. And those rules tell us that time is flexible, relative, dependent on motion. Your willingness to engage with this strangeness, to push through the discomfort of counterintuitive ideas, that is the spirit of science. That is how we grow in our understanding. Now you might be wondering, is this just theory? Is this just mathematics on paper? How do we know time dilation actually happens in the real world? This is where the story gets even more exciting, because we have tested time dilation countless times in countless ways, and every single test has confirmed Einstein's predictions with extraordinary precision. Let me tell you about some of the most famous experiments. In 1971, two physicists named Joseph Hafele and Richard Keating performed an elegant test of time dilation. They took 4 cesium atomic clocks, among the most precise timekeeping devices ever created, and put them on commercial airline flights. 2 clocks flew eastward around the world, 2 clocks flew westward around the world. Meanwhile, reference clocks stayed on the ground at the United States Naval Observatory. After the flights, they compared all the clocks. Now, why does the direction of flight matter? The Earth is rotating. A clock on the ground at the equator is already moving eastward at about 1,600 kilometers per hour. A plane flying east is moving even faster relative to the underlying space-time. A plane flying west is moving slower relative to space-time because it is flying against the Earth's rotation. According to Einstein's theory, the eastbound clocks should have experienced more time dilation because they were moving faster. The westbound clocks should have experienced less time dilation because they were moving slower. The results matched the predictions to within the experimental uncertainty. The eastbound clocks lost about 59 nanoseconds compared to the ground clocks. The westbound clocks gained about 273 nanoseconds. These are tiny amounts, billionths of a second, but the atomic clocks were precise enough to measure them. Einstein's theory, proposed decades earlier from pure thought experiments, just was confirmed by actual clocks flying on actual planes. Reality obeys the equations. There is another confirmation that happens every day, all around us, in the form of particles called muons. Muons are created when cosmic rays from deep space collide with atoms in Earth's upper atmosphere. These collisions happen about 10 kilometers above the surface. Muons are unstable particles with a very short half-life, about 2.2 microseconds. In that time, even traveling at nearly the speed of light, a muon should only be able to travel about 660 meters before decaying. They should never reach the ground. They should decay while still high in the atmosphere, but muons do reach the ground. We detect them constantly. Thousands of muons pass through your body every minute. How is this possible? Time dilation. The muons are traveling at roughly 99.9% the speed of light. At this speed, their internal clocks run much slower from our perspective. Their 2.2 microsecond half-life is stretched out to dozens of microseconds. This gives them enough time to reach the surface before decaying. From the muons' perspective, something different but equally valid happens. They experience their normal 2.2 microsecond half-life. But from their perspective, the distance to Earth's surface is length contracted, shortened by the same Lorentz factor. The mountain is much thinner in the muons' reference frame. Either way you analyze it, the muon reaches the ground. Both perspectives, time dilation for us or length contraction for the muon, give the same answer. This is not a coincidence. It is the beautiful consistency of relativistic physics. Perhaps the most impactful confirmation of time dilation is the global positioning system that guides your phone, your car, and countless other devices. The GPS constellation consists of around 30 satellites orbiting Earth at an altitude of about 20,000 kilometers. These satellites carry atomic clocks that must be incredibly precise to provide accurate positioning. The system works by measuring the tiny differences in signal arrival times from multiple satellites and triangulating your position. For GPS to work, the clocks on the satellites must agree with clocks on the ground to within about 30 nanoseconds. Any greater discrepancy in the positioning errors would become unacceptable. But the satellites experience two relativistic effects. First, they are moving at about 14,000 kilometers per hour relative to the ground. This velocity causes time dilation. The satellite clocks run slower than ground clocks by about 7 microseconds per day. Second, the satellites are higher in Earth's gravitational field than ground clocks. Gravity also affects time, something we will discuss shortly. This gravitational effect makes the satellite clocks run faster than ground clocks by about 45 microseconds per day. The net effect is that satellite clocks run faster by about 38 microseconds per day. If these relativistic corrections were not programmed into the GPS system, the positioning errors would accumulate rapidly. Within about 2 minutes, the errors would be noticeable. Within a day, your GPS would be wrong by about 10 kilometers. Within a week, navigation would be useless. Every time you use GPS to find your location, you're relying on Einstein's theories being correct. Every accurate position fix is a confirmation of relativity. You carry a relativistic physics experiment in your pocket. Astronauts on the International Space Station also experience measurable time dilation. The ISS orbits Earth at about 28,000 kilometers per hour, at an altitude of about 400 kilometers. The velocity effect makes their clocks run slower, but the lower gravity at that altitude makes their clocks run faster. The velocity effect dominates slightly, so ISS astronauts age a tiny bit slower than people on Earth. After 6 months in space, an astronaut is about 0.005 seconds younger than they would have been had they stayed on Earth. It is a trivially small amount, but it is real and measurable. NASA conducted a fascinating study with astronaut Scott Kelly and his identical twin brother Mark Kelly. Scott spent 340 days aboard the ISS while Mark remained on Earth. This was not primarily a test of time dilation, as the effect would be far too small to detect biologically. The study focused on the health effects of long-duration spaceflight, but it captured the public imagination as a real-life twin paradox, albeit one where the time difference was imperceptible. Speaking of the twin paradox, this is one of the most famous and most confusing aspects of time dilation. Let me explain it carefully, because understanding why it is not actually a paradox reveals deep truths about the nature of relativity. Here is the setup. Two twins, Alice and Bob, are born at the same time on Earth. They're exactly the same age. When they turn 25, Alice boards a spacecraft and travels to a distant star at 80% the speed of light. The star is 4 light years away. Alice travels there, turns around, and travels back at the same speed. Meanwhile, Bob stays on Earth. When Alice returns, how old is each twin? Let us calculate from Bob's perspective on Earth. He sees Alice travel 4 light years at 80% light speed. At this speed, the journey takes 5 years. Then Alice turns around and travels 4 light years back, which takes another 5 years. Total round-trip time as measured by Bob, 10 years. So when Alice returns, Bob is 35 years old, 10 years older than when she left. But Alice is moving at 80% light speed, and at this speed the Lorentz factor is 1.67. Time for Alice passes at only 60% the rate of time for Bob. So during what Bob sees as a 10-year journey, Alice experiences only 6 years. When she returns, she is 31 years old. She's 4 years younger than her twin brother. This is the twin paradox setup, and so far everything seems straightforward. But here is where the apparent paradox arises. From Alice's perspective, she was sitting still in her spacecraft, and it was Earth, along with Bob, that zoomed away at 80% light speed and then returned. Motion is relative, after all. If motion is truly relative, why can't Alice claim that Bob was the one moving, and therefore Bob should be the one who aged less? If both perspectives are equally valid, how can there be an asymmetry in their ages when they reunite? This seems like a contradiction. This is what makes it a paradox, but it is not actually a paradox. There is a crucial asymmetry that breaks the apparent symmetry. Alice accelerated. Bob did not. Alice started at rest on Earth, accelerated to 80% light speed, travelled to the star, decelerated, stopped, turned around, accelerated again back to 80% light speed, travelled back to Earth, and decelerated to a stop. Bob just floated along on Earth, experiencing no acceleration whatsoever. Remember Einstein's first postulate. The laws of physics are the same in all inertial reference frames. An inertial reference frame is one that is not accelerating. Bob's reference frame is inertial throughout the entire experiment. He never accelerates. Alice's reference frame is not inertial. She accelerates multiple times during her journey. This breaks the symmetry. Alice knows she accelerated. She felt it. Her coffee sloshed around. Objects pressed against the back of her spacecraft during acceleration. There is no ambiguity about who accelerated and who did not. When you carefully analyze the situation using the full machinery of special relativity, accounting for the effects of acceleration and the shifting of simultaneity that occurs when you change reference frames, you find that Alice unambiguously ages less than Bob. The calculation we did from Bob's perspective is correct. There is no contradiction. The apparent paradox dissolves when you recognize that the two situations are not symmetric. Let me describe what this looks like from Alice's perspective in more detail, because this is where the resolution becomes clear. When Alice is travelling away from Earth, she looks back and sees Bob's clocks running slow, just as relativity predicts. From her moving frame, Bob is the one experiencing time dilation. So far, so symmetric. But then Alice turns around. This turnaround involves acceleration. During this acceleration, something dramatic happens to Alice's notion of simultaneity. The concept of now, of what is happening on Earth at this very moment, shifts radically. Before the turnaround, events on Earth that Alice considers simultaneous with herself are relatively recent. After the turnaround, events on Earth that Alice considers simultaneous with herself are much further in the future. It is as if a huge chunk of time on Earth fast-forwarded during Alice's acceleration. This shift in simultaneity accounts for the extra time that passes on Earth. From Alice's perspective, yes, Bob's clocks ran slow during both legs of the journey. But during the turnaround, Bob's time jumped forward enormously. The net result is that more time passed for Bob than for Alice, exactly matching the calculation from Bob's perspective. This resolution of the twin paradox has been confirmed experimentally, at least for particles and atomic clocks. The Hafele-Keating experiment I mentioned earlier was essentially a test of the twin paradox. The eastbound clocks, which experienced more total acceleration from the perspective of the underlying spacetime, showed the predicted time differences. Particle physics experiments confirm that accelerated particles and non-accelerated particles have different proper times, exactly as relativity predicts. The twin paradox is not a paradox at all. It is a beautiful illustration of how consistently relativity treats space and time. Now I want to expand our understanding further by introducing another way that time can be affected. So far, we have focused on velocity and special relativity, but Einstein did not stop there. 10 years after special relativity in 1915, he completed his masterpiece, the general theory of relativity. And general relativity revealed that gravity also affects the flow of time. Einstein began with what he called the equivalence principle. He noticed that the experience of gravity and the experience of acceleration are indistinguishable. If you are in a closed room and you feel a force pulling you toward the floor, you cannot tell whether you're standing on a planet with gravity or whether you're in a spacecraft accelerating upward at 1g. The experiences are identical. Einstein proposed that they are identical because they are, in some deep sense, the same thing. This insight led him to reconceive gravity not as a force pulling objects together, but as the curvature of space-time caused by mass and energy. Massive objects like the Earth do not reach out and pull on you with an invisible force. Instead, they curve the space-time around them. You, moving through this curved space-time, follow the straightest possible path, which happens to curve toward the massive object. What we perceive as the force of gravity is actually the geometry of space-time guiding our motion. And here is the key point for our discussion. Curved space-time does not just affect the paths of objects through space. It affects the passage of time. Time runs slower in stronger gravitational fields. This is called gravitational time dilation, and it is separate from and additional to the velocity-based time dilation we have been discussing. The formula for gravitational time dilation involves the gravitational potential at your location. Near a massive object, deep in its gravitational well, time runs slower. Far from any massive object, in the flat space-time of empty space, time runs faster. The strength of this effect depends on how deep you are in the gravity well and how strong the gravity is. On the surface of the Earth, time runs slightly slower than it does in orbit or in deep space. The difference is tiny, only about 1 part in a billion, but it is real and measurable. Clocks at the top of a mountain run slightly faster than clocks at sea level. This has been confirmed with exquisitely precise atomic clocks. A clock elevated by just 1 meter runs faster by about 1 part in 10 to the 16th power. Tiny, but detectable with modern technology. Near much more massive objects, the effect becomes dramatic. On the surface of a neutron star, where gravity is billions of times stronger than on Earth, time runs significantly slower. Near the event horizon of a black hole, the effect becomes extreme. As you approach the event horizon, time from the perspective of a distant observer slows down asymptotically. At the event horizon itself, from a distant perspective, time stops entirely. You would appear to freeze at the edge of the black hole. Never quite falling in, your image redshifting into invisibility as your time grinds to a halt. From your own perspective, falling into the black hole, you would experience time normally. You would cross the event horizon without any fanfare, continuing to fall toward the singularity at the center. Your clocks would tick normally by your reckoning, but communication with the outside universe would become impossible. You would fall into a region where time itself points toward the singularity, where the future is not ahead of you in time but inward in space. You may have seen the movie Interstellar, which depicts gravitational time dilation dramatically. In the film, astronauts visit a planet orbiting very close to a massive black hole named Gargantua. On this planet, 1 hour equals 7 years on Earth. The astronauts spend a few hours on the surface and return to their ship to find that their colleague who stayed behind has aged 23 years. This scenario is scientifically plausible, though achieving such extreme time dilation would require a planet impossibly close to the event horizon of a supermassive, rapidly spinning black hole. The film consulted with Nobel Prize-winning physicist Kip Thorne to ensure scientific accuracy, and the time dilation depicted, while extreme, is consistent with general relativity. So we now have 2 separate mechanisms for time dilation. Moving fast through space causes time to slow down, as described by special relativity. Being in a strong gravitational field also causes time to slow down, as described by general relativity. In most real situations, both effects are present simultaneously. For the GPS satellites, as I mentioned earlier, both effects are at play. The velocity effect makes the satellite clocks run slower by about 7 microseconds per day. The gravitational effect, because the satellites are higher and in a weaker gravitational field, makes them run faster by about 45 microseconds per day. The net result is that the satellite clocks run faster by about 38 microseconds per day. Both effects must be accounted for to achieve accurate positioning. For astronauts on the International Space Station, the situation is similar but opposite. The ISS is moving fast, which slows time, but it is also higher up and in a weaker gravitational field, which speeds time. At the ISS's altitude and velocity, the velocity effect dominates slightly. ISS astronauts age a tiny bit slower than people on Earth. If the ISS were higher, like the GPS satellites, the gravitational effect would dominate, and astronauts would age slightly faster. For future interstellar travelers, both effects will need to be carefully considered. A spacecraft accelerating at 1g, which would feel like normal Earth gravity, would experience gravitational time dilation effects, as well as velocity-based effects. The calculations become complex, but the physics is well understood. Let me take a moment here to share something important. If you have stayed with me this long, I truly appreciate your attention and curiosity. We have covered a lot of ground, from Einstein's revolutionary insights to the mathematics of time dilation, to experimental confirmations to the resolution of famous paradoxes. But now I want to pivot toward a different kind of question. A question about the future. What does time dilation mean for the future of humanity and space? Consider the challenges of interstellar travel. The nearest star system to our Sun is Alpha Centauri, about 4.4 light-years away. At the fastest speeds we have ever achieved with a spacecraft, it would take tens of thousands of years to reach Alpha Centauri. This is clearly impractical. No one is going to wait tens of thousands of years for their spacecraft to arrive. But what if we could go faster? Much faster. What if we could approach the speed of light? Suddenly the calculations change dramatically. Not because the travel time measured by Earth changes very much, but because the travel time measured by the astronauts shrinks drastically due to time dilation. Let us say we develop a spacecraft capable of traveling at 90% the speed of light. At this speed, the journey to Alpha Centauri takes about 4.9 years as measured from Earth. But the astronauts on board, experiencing time dilation with a Lorentz Factor of about 2.3, experience only about 2.1 years. Not bad for an interstellar journey. Push the speed higher. At 99% light speed, the Earth time to Alpha Centauri is about 4.4 years, but ship time is only about 7.5 months. You could leave Earth, travel to another star, and arrive feeling like less than a year has passed. At 99.9% light speed, ship time drops to about 3 weeks. At 99.99% less than 3 days. The faster you go, the more time compression you experience. From the traveler's perspective, the universe shrinks. Distances that would take centuries to cross at normal speeds become accessible within a human lifetime. This has profound implications for the colonization of the galaxy. Imagine a future where relativistic travel is possible. You could leave Earth, travel to a star 50 light-years away at 99% the speed of light, experience about 7 years of ship time, and arrive at your destination. You would be 7 years older. You would have 7 years of memories from the journey. But on Earth, 50 years would have passed. Everyone you knew would have aged half a century. The world you left behind would be almost unrecognizable. This is the trade-off of relativistic travel. You gain time personally. You experience fewer years than everyone else. In a sense, you travel to the future. But you cannot travel back. You cannot undo the years that passed on Earth. You cannot return to the moment you left. The one-way nature of this time travel, this journey into the future, means permanent separation from your own era. Would you make such a choice? Would you board a spacecraft knowing that everyone you love would age decades or centuries while you aged only years? Knowing that you would step out onto a new world or back onto Earth to find a society utterly transformed? Knowing that you could never go back, never see your home as it was, never reunite with your generation? Some would say no. The price is too high, the loneliness too profound. Why live a few extra subjective years if everyone you care about is gone? But others would say yes. The universe is vast and filled with wonders. The chance to see distant stars, alien worlds, the far future of human civilization, these opportunities might be worth any price. Explorers have always left home knowing they might never return. Relativistic travelers would simply take this to an extreme. There is a concept in science fiction called a generation ship. This is a spacecraft so large and self-sustaining that generations of humans could live and die on board during an interstellar journey. Your great-great-grandchildren might be the ones to finally arrive at the destination. It is a way of crossing interstellar distances without relativistic speeds, by accepting that the journey will take longer than a human lifetime. Relativistic travel offers an alternative. Instead of generations of travelers, a single traveler can make the journey. Time dilation compresses the trip into a bearable duration. The cost is not generations of shipboard life. The cost is temporal disconnection from everyone who did not make the journey. Let me walk you through some specific scenarios to make this concrete. Scenario 1, a mission to Alpha Centauri at 50% the speed of light. Earth time for the journey, about 8.8 years each way, 17.6 years round trip. Ship time, about 7.6 years each way, 15.2 years round trip. An astronaut leaving at age 30 would return at age 45 in their own reckoning, but Earth would be about 17.5 years older. Not too extreme. Friends and family would be noticeably older but still recognizable. This is perhaps the most human scale of relativistic travel. Scenario 2, a mission to a star 20 light-years away at 90% the speed of light. Earth time about 22 years each way, 44 years round trip. Ship time about 9.6 years each way, about 19 years round trip. An astronaut leaving at age 30 would return at about age 49. But Earth would be 44 years older. The astronaut's own children, if they had any, might be older than the astronaut now is. Parents would likely have passed away. The world would have changed through nearly half a century of history. Scenario 3. A mission to a star 100. Light-years away at 99% the speed of light. Earth time, about 101 years each way, 202 years round trip. Ship time, about 14 years each way, about 28 years round trip. An astronaut leaving at age 30 would return at about age 58, still middle-aged, still with many years ahead, but Earth would be 2 centuries older, 200 years of history, 8 generations of change. No one alive when you left would still be alive when you returned. Your home country might not exist. Your language might have evolved into something barely recognizable. You would be an artifact from the past, stepping into a future you cannot predict or control. Scenario 4. A mission to the center of the Milky Way galaxy, about 26,000 light-years away, at 99.9999% the speed of light. Ship time, about a decade each way, but Earth time, about 26,000 years each way. You would leave Earth in the 21st century and return in the year 54,000 or so. Human civilization would be either unimaginably advanced or long extinct. No one could predict what you would find. You would be a time capsule from a distant past, emerging into a future beyond comprehension. The mathematics allows for even more extreme scenarios. Approach close enough to the speed of light, and you could cross the observable universe in a single human lifetime by your own reckoning. The rest of the universe would age billions of years. You could, in principle, witness the heat death of the cosmos, the end of all things, and still be a biological organism when you arrive. The engineering challenges are beyond anything we can currently imagine, but the physics does not forbid it. Of course. There are enormous practical challenges to achieving relativistic speeds. Let us be realistic about what we would need. First, energy. Accelerating a spacecraft to relativistic speeds requires stupendous amounts of energy. The faster you want to go, the more energy you need, and the relationship is not linear. As you approach the speed of light, the energy required approaches infinity. Even reaching 10% of the speed of light would require more energy than humanity currently produces in a year. Reaching 90% would require orders of magnitude more. We do not currently have any propulsion technology capable of delivering these energies. Second, fuel. Conventional rockets carry their fuel with them, which means the fuel itself has mass that must also be accelerated. This leads to the rocket equation, which shows that the amount of fuel needed grows exponentially with the desired velocity change. For relativistic speeds, the fuel requirements become absurd. You would need mountains of fuel to accelerate a small payload. Various proposed solutions include collecting fuel in transit, using external power sources like lasers to accelerate the craft, or finding more energetic fuels like antimatter. Third, radiation and particle collisions. Space is not perfectly empty. It contains a thin soup of hydrogen atoms, dust particles, and radiation. At low speeds, these are irrelevant. But at relativistic speeds, every hydrogen atom becomes a deadly bullet. The kinetic energy of impact scales with velocity squared, and at near-light speeds, even a stray hydrogen atom carries enormous energy. A spacecraft traveling at 99% light speed would need shielding capable of withstanding a continuous bombardment of high-energy particles. This shielding would add mass, requiring more energy, which requires more fuel, which adds more mass. The engineering challenges cascade. Fourth, deceleration. Getting up to speed is only half the problem. You also need to slow down when you arrive. This doubles the energy requirements at minimum. If you accelerate halfway and decelerate halfway, the journey takes longer and you experience less extreme time dilation. If you accelerate to high speed and then need to decelerate quickly at the destination, you need to carry fuel for braking or find some other way to shed velocity. Despite these challenges, scientists and engineers have proposed various schemes for interstellar travel. Fine, let me mention a few. Nuclear pulse propulsion, the idea behind Project Orion from the 1950s and 60s, would propel a spacecraft by detonating nuclear bombs behind it. The ship would ride the shockwaves, gradually accelerating. With enough bombs and enough time, significant fractions of light speed might be achievable. The obvious drawbacks include the need for vast numbers of nuclear weapons, the radiation hazards, and the political challenges. Antimatter propulsion offers the highest possible energy density. When matter meets antimatter, 100% of their mass converts to energy, compared to less than 1% in nuclear reactions. An antimatter rocket could theoretically achieve relativistic speeds. The challenges include producing antimatter, which currently costs trillions of dollars per gram, storing antimatter safely, and designing an engine that can harness the annihilation energy. Laser sails, the concept behind the Breakthrough Starshot initiative, would use powerful lasers on Earth to accelerate tiny, lightweight spacecraft with reflective sails. The craft themselves carry no fuel, all the energy comes from the lasers. This approach could potentially accelerate small probes to 20% of light speed, enough to reach Alpha Centauri in about 20 years. The challenges include building sufficiently powerful lasers, keeping the beam focused over vast distances, and fitting useful instruments into a gram-scale probe. Fusion propulsion, using controlled nuclear fusion reactions to generate thrust, could potentially achieve a few percent of light speed. This would not give significant time dilation effects, but could make interstellar journeys feasible within centuries rather than millennia. The challenge is that we have not yet achieved sustained fusion power on Earth, let alone in a compact spacecraft engine. These are all speculative technologies, some more plausible than others, but the underlying physics of time dilation is solid. If we ever do develop the technology to travel at relativistic speeds, time dilation will be a real effect that relativistic travelers will experience. The mathematics is certain, only the engineering remains to be solved. Let me now push into some more extreme territory. Let us explore scenarios at the very edge of what physics allows. What would it be like to travel at 99.99999% the speed of light? At this speed, the Lorentz Factor is about 70,000. For every day you experience, nearly 200 years pass in the outside universe. You could eat breakfast, watch a movie, take a nap, eat dinner, and by the time you go to sleep, 600 years have elapsed on Earth. Civilizations rise and fall between your meals. What would you see, looking out the window of such a spacecraft? The view would be profoundly strange. Due to relativistic aberration, light from all directions would be compressed toward the direction you are traveling. The stars ahead would cluster together into a bright point. The stars behind would be invisible, red-shifted into non-existence. The universe would appear as a tunnel of light ahead, a void behind. The light you see would also be Doppler-shifted. Stars ahead would be blue-shifted, their light compressed to higher frequencies. What was visible light would become ultraviolet, then X-rays, then gamma rays. You would need special shielding and sensors to see anything at all. Stars behind would be red-shifted into radio waves, then invisible. The cosmic microwave background radiation would be blue-shifted to dangerous levels ahead, red-shifted away to nothing behind. The universe would look nothing like it does from Earth. What would a photon experience, if we can even ask such a question? Photons travel at exactly the speed of light. Their Lorentz factor is infinite. From a photon's reference frame, if the concept even applies, no time passes whatsoever. A photon emitted from a distant quasar 12 billion years ago, from our perspective, arrives at Earth having experienced no time at all. The emission and absorption are simultaneous from the photon's perspective. The photon does not age. It does not experience the journey. For light, all moments are one moment. The universe is a single instant, infinitely contracted along the direction of travel. There is something profound here, something that brushes against the deepest questions of existence. What is time, really? If it can run at different rates for different observers, if it can slow to nothing for a photon, is it fundamental, or is it emergent, arising from something more basic? Physicists still debate these questions. Time might be woven into the fabric of reality at the most fundamental level. Or it might be an illusion, a convenient way for beings like us to organize our experiences, but not a true feature of ultimate reality. The block universe interpretation of relativity suggests that past, present, and future all exist equally. The universe is a four-dimensional block, static and eternal, containing all of space-time at once. What we experience as the flow of time, the sensation of the present moving from past to future, is an illusion. In this view, your birth and your death both exist, timelessly, in the eternal block of space-time. There is no objective now. Every moment is equally real. This interpretation is consistent with the physics of relativity, which shows that simultaneity is relative. Two events that are simultaneous from one perspective are not simultaneous from another. There is no universal present moment that all observers share. If the present is not universal, if different observers disagree about what is happening now, then perhaps now is not a fundamental feature of reality. Perhaps all times exist with equal validity. I find these ideas both disturbing and beautiful. Disturbing because they challenge our deepest intuitions about time, about the flow of experience, about the meaning of life and death. Beautiful because they hint at a reality far stranger and more wonderful than our everyday experience suggests. But let us return from these philosophical heights to something more concrete. Let us talk about what time dilation means for you, personally, today. You cannot currently travel at relativistic speeds. The fastest humans have ever traveled was the Apollo astronauts returning from the moon at about 40,000 kilometers per hour. This is about 0.004% of the speed of light. The time dilation effect at this speed is completely negligible, but you're still experiencing time dilation right now, just in tiny amounts. If you're on an airplane, you're experiencing a fraction of a nanosecond of time dilation during your flight. If you live at a higher elevation than your friend, your clocks run slightly faster due to gravitational time dilation. These effects are real, they are there, but they are far too small to notice or to meaningfully affect your life. The practical impact of time dilation on your life comes through technology. GPS relies on relativistic corrections. Particle accelerators, which produce medical isotopes and enable fundamental research, must account for the extended lifetimes of fast-moving particles. The electronics industry benefits from insights derived from relativistic physics. In subtle, indirect ways, time dilation affects your life every day. And there is another way time dilation affects you. It affects how you understand your place in the universe. You are not living in a simple clockwork cosmos where time ticks uniformly for everyone. You are living in a relativistic universe where time is flexible, where the rate of aging depends on how fast you move and how deep you are in a gravity well. Every second of your life is a second experienced at a specific rate, a rate that would be different if your circumstances were different. When you look at the stars at night, you're seeing light that left those stars years or centuries or millennia ago. You're seeing the past, but the light itself, the photons entering your eyes, experience no time during their journey. They left the star and arrived at your retina in the same instant from their perspective. You're being touched by timeless messengers from the past. When you think about astronauts on the International Space Station, you can know that they are aging slightly slower than you are right now at this very moment. The difference is tiny, but it is real. They will return to Earth fractionally younger than they would have been had they stayed home. When you imagine the future of humanity, you can picture a civilization that spreads across the galaxy using relativistic spacecraft. Travelers who leave for distant stars, experiencing years while Earth experiences centuries. Colonies connected not by real-time communication, but by light-speed messages and relativistic travelers. All of them embedded in the strange elastic time of Einstein's universe. I want to address some common questions and misconceptions that people have about time dilation. People often ask whether time dilation is a real physical effect or just an artifact of measurement. The answer is unambiguous. Time dilation is real. It is not a matter of clocks running slow due to mechanical effects. The actual passage of time, the ticking of physical processes at the atomic level, changes with velocity and gravity. An astronaut returning from a high-speed journey is genuinely younger than they would have been. Their heart has beaten fewer times. Their cells have divided fewer times. Their biological age is less. This is not an illusion or a measurement artifact. It is reality. People often wonder whether you would feel time dilation while experiencing it. The answer is no. Your experience of time is always normal from your own perspective. You cannot feel time running slow because all your processes, including your thoughts and perceptions, are equally slowed. From your perspective, nothing seems different. It is only when you compare your clocks to those of someone in a different reference frame that the difference becomes apparent. People sometimes ask whether time dilation could be used to travel backward in time. The answer is no, at least not through the mechanisms we have discussed. Velocity-based and gravitational time dilation only allow you to travel forward in time relative to others. You can age slower than someone else, arriving at future dates having experienced less personal time. But you cannot return to the past. You cannot revisit moments that have already occurred. Forward time travel is physics. Backward time travel remains in the realm of speculation and science fiction. There are theoretical ideas about how backward time travel might work, involving wormholes or cosmic strings or closed time-like curves. These are mathematically valid solutions to Einstein's equations, but they require exotic conditions that may not exist in our universe, such as negative energy densities or matter arranged in impossible configurations. Most physicists are skeptical that backward time travel is actually possible, though we cannot rule it out with complete certainty. People ask what happens if two spaceships pass each other at relativistic speeds. Each sees the other as time dilated, with the other's clocks running slow. How can both be correct? The answer is that both are correct in their respective reference frames. There is no contradiction because the two observers are in different frames of reference, and there is no absolute truth about whose time is really running slow. The situation is symmetric as long as no acceleration occurs. If one of them later decelerates and compares clocks, the comparison will depend on the details of who accelerated and how. The resolution is consistent with everything we have discussed. Let me share a thought experiment that sometimes confuses people. Imagine you are watching a clock on a moving spaceship. You see it ticking slowly due to time dilation, but the clock itself, from its own perspective, is ticking normally. Now imagine there is a bomb attached to the clock set to explode after 1 hour of clock time. From your perspective, the clock is running slow, so it takes more than an hour of your time before the bomb explodes. From the clock's perspective, exactly 1 hour passes and then it explodes. Both perspectives are consistent. The event, the explosion, happens once. But the time at which it happens, measured in different reference frames, differs. The physics is consistent. The explosion occurs when the clock reads 1 hour, which corresponds to different times in different frames. Another question that arises is whether time dilation affects the speed of light itself. The answer is no. The speed of light is invariant, the same for all observers. This is the foundation of relativity. Light always travels at about 300,000 kilometers per second in vacuum, regardless of the motion of the source or the observer. Time dilation and length contraction arise precisely to preserve this invariance. Light does not slow down or speed up. Time and space adjust to keep light constant. Let me bring all of this together and reflect on what we have learned. We began with a simple question. Why does traveling fast make you age slower? We have now seen the full answer, in all its strange and beautiful detail. The story starts with a young patent clerk named Albert Einstein, who dared to take the constancy of light speed seriously. If light always travels at the same speed regardless of how you are moving, then time and space themselves must be flexible. This insight led to the special theory of relativity, which revealed that time dilates for moving observers. The faster you move through space, the slower you move through time. We explored the mathematics of time dilation, seeing how the Lorentz Factor determines the relationship between different observers' times. We saw that at everyday speeds the effect is negligible, but as you approach light speed, time dilation becomes extreme. At 99% light speed, time runs at 14% its normal rate. At 99.99%, time nearly stops. We saw that this is not mere theory but proven fact. The Hafele-Keating experiment demonstrated time dilation with clocks on airplanes. Muons from cosmic rays survive their journey to Earth because time slows down for them. GPS satellites require relativistic corrections to function. Astronauts on the ISS age measurably slower than people on Earth. Time dilation is woven into the technology we use every day. We resolve the twin paradox, the understanding that acceleration breaks the symmetry between two observers. The twin who stays home ages more than the twin who travels, not because of any paradox, but because the traveling twin's journey involves acceleration that the stay-at-home twin does not experience. We expanded our view to include gravitational time dilation, the effect predicted by general relativity. Gravity curves space-time, and time runs slower in stronger gravitational fields. This effect combines with velocity-based time dilation in real situations like GPS satellites and astronauts in orbit. We imagined the future of interstellar travel, where relativistic spacecraft could compress journeys across light years into human-scale experiences. We confronted the cost of such travel, the temporal disconnection from everyone who stays behind. We considered the engineering challenges that must be overcome to achieve such speeds. We pushed to the extremes, imagining travel at nearly light speed, where the universe contracts and time nearly stops. We contemplated the timeless existence of photons, for whom all moments are one moment. We touched on philosophical questions about the nature of time itself. What does all this mean for you? It means you are living in a universe far stranger than common sense suggests. Time is not a river flowing uniformly for everyone. It is a local phenomenon, running at different rates in different places and for different observers. Your experience of time, this moment right now, is shaped by your location in space and your motion through it. It means that the laws of physics, properly understood, allow for possibilities that sound like magic. Traveling to the future is possible. Staying young while others grow old is possible. Crossing vast distances of space within a human lifetime is possible. These are not fantasies. They are implications of physics that has been tested and confirmed for over a century. It means that human destiny among the stars, if we ever achieve it, will be shaped by the strange geometry of space-time. Interstellar travelers will be temporally isolated from Earth. Colonies will develop independently, separated by light years and effectively by centuries. Communication will be slow, relativistic travel will be one way into the future, and the human diaspora across the galaxy will fracture into countless cultures evolving independently. It means that the universe rewards the curious, those who are willing to ask questions, to follow the logic wherever it leads, to embrace conclusions that violate intuition but satisfy evidence. The universe does not owe us a simple or comfortable reality. It owes us nothing but the opportunity to discover whatever truths we are clever enough to find. I hope this journey has sparked something in you. A sense of wonder, perhaps, a desire to learn more, a new way of seeing your place in the cosmos. You have spent this time with me exploring one of the deepest truths about reality. That is not nothing. That is a choice to expand your mind, to wrestle with difficult ideas, to grow in understanding. If this video has meant something to you, if you have learned something you did not know, if your perspective has shifted even slightly, I would be grateful if you would let me know. Leave a comment sharing what surprised you the most. Like the video so others can find it. Subscribe to the channel so we can continue exploring the universe together. Share this with someone who thinks physics is boring or irrelevant. Show them that physics is the key to understanding reality itself. There is so much more to explore. Black holes, where time dilation reaches infinite extremes. Wormholes, hypothetical tunnels through space-time. The quantum nature of time, which remains deeply mysterious. The arrow of time, why the future is different from the past. Each of these topics deserves its own deep dive, and perhaps we will take those journeys together. For now, I want to leave you with this thought. The next time you look at your watch, the next time you feel a second pass, remember that someone, somewhere, moving faster than you is experiencing time more slowly at that very moment. Astronauts overhead are aging slower. Particles in accelerators are frozen in slow motion. Photons from distant stars are experiencing no time at all. You are embedded in a relativistic universe, where time is not what it seems, where reality is stranger than fiction, where the truth is more wonderful than any myth. Keep looking up. Keep questioning everything. Keep following your curiosity wherever it leads. The universe is waiting to be understood, and every question you ask brings us one step closer to comprehending the incomprehensible. Until next time, remember that you are a collection of atoms, temporarily assembled into a pattern that can wonder about time itself. That is a privilege beyond measure. Use it well. Thank you for watching. Thank you for thinking. Thank you for being curious. I will see you in the next exploration of the cosmos. And remember, time is not waiting for any of us. End.